So today's topic is based on the electro-optic modulators. Now, under this electro-optic, uh, there are several modulators: electro-optic modulators, acoustic optic modulators, and magneto-optic modulators. So I will discuss one by one. Now, what is electro-optic effect? So basically, electro-optic effect that can be observed when light propagates through a crystal in the presence of an electric field. Now, the electric field which is applied to the crystal that can alter or induce birefringence by changing the refractive index of the medium. And this effect is called as electro-optic effect. Now, there are two types of electro-optic effect. One is the Pockels effect, or it is also called the linear electro-optic effect. Another is the Kerr effect, or non-linear electro-optic effect. So in Pockels effect, that is observed only in non-centrosymmetric material, and here the change in the refractive index, that is the del mu, which is proportional to the applied electric field E. Now we can write it using this equation. And since the change is very small, so by using the Taylor series, that can be written as this one. The equation can be written as this one. Okay, so here the R, basically it is called as electro-optic coefficient of the medium, or it is also called as electro-optic constant of the medium. And this is the Kerr effect. Okay, 1 minute. Okay, so Kerr effect, which is basically a nonlinear electro-optic effect, here the change in the refractive index, that is proportional to the square of the applied electric field, and that can be written as this one. So here also the change is very small. That's why it is expressed in Taylor series, and the equation can be written as this one. Okay, where this S is called the Kerr constant of the material. Now this Kerr effect, this is very weak compared to the Pockels effect. Now some highly transparent crystals that show the Kerr effect, but with smaller Kerr constant, this S will be very small. And also some polar liquids such as nitro toluene or nitrobenzene that show appreciable Kerr value. Now the change in the refractive index, which induces or alters the birefringence of the crystal, and therefore the beam that suffers a phase shift. Even though the change in the refractive index is very small, the corresponding phase change in the beam propagating along the direction of the applied electric field, that could be significant. Okay. Now, electro-optic materials. So here the list of materials which are frequently used as non-linear crystal material, and these are like potassium dideuterium phosphate or ammonium dihydrogen phosphate, potassium titanyl phosphate, beta barium borate, lithium niobate, niobate, and lithium tantal. So these are the electro-optic materials which are used as a non-linear crystal. And I have already told you about the uh, electro-optic materials, which shows this car constant, and nitrotoluene and benzene is there. And these are the previously these are used as they show the Pockels effect. Now the application where these electro-optic modulators can be used, or this effect can be seen, like a beam of light propagating through the crystal that is subjected to an electric field which suffers a phase shift, as I have told you earlier, due to Pockels effect, and it is very useful for phase modulation. Okay, and under certain configurations or geometrical conditions, the applied electric field acts differently on uh, two linearly polarized light waves, which passes through the crystal, and therefore it can be used to introduce an electric field dependent between the two polarizations, and this effect that can be used to control the amplitude of the light beam in accordance with the applied electric field, which is used in amplitude modulation technique. This electro-optic uh, effect that is useful for imposing information on a light beam, which is basically called the electro-optic modulation, that is very useful in optical communications. This is also used in modulating the power of a laser beam for laser printing and high-speed digital data recording purpose. Also, this principle is used to um, apply in electro-optic sensors. Now, there are three types of electro-optic modulators. One is the phase modulator, another is the polarization modulator, another is the amplitude modulator. Now, in phase modulators, so this is the simplest type of electro-optic modulator, which is basically a phase modulator containing only a pocket cell, and where an electric field that changes the phase relay of a laser beam, which is sent through the uh, crystal. Okay, and the polarization of the uh, input beam that is often has to align with the optical axis of that crystal, so that the polarization state that is not changed anytime. In case of polarization modulators, so it depends on the type and orientation of the nonlinear crystal basically, and on the direction of the applied electric field, the phase delay that can depend on the polarization direction. And a Pockels cell can thus be seen as voltage control waveplate, and it can be used uh, for modulating the polarization state. For a linear input polarization purpose, the output polarization will in general be elliptical in nature rather than the simply linear polarization. What happened, it is in polarization state with rotated direction. And in amplitude modulators, So it is uh, combined with other optical elements in particular with the polarizers and analyzers. So here also the pocket cells are used to uh, perform the modulation technique. Now in particular an amplitude modulator that is based on a pocket cells for modifying the polarization state, and an analyzer for subsequently converting this into a change into a transmitted optical amplitude as well as the power. So these are the functions of uh, different modulators. Now coming to the magneto-optic effect, so it is basically the result of an interaction between light and the magnetic field within the magneto-optic medium. Now these are divided into three main categories related to this transmission, reflection, and absorption of light. So I will discuss one by one. Transmission mode. So here the Faraday effect occurs. Now the rotation uh, of a polarization plane of a linearly polarized light during its propagation through a layer of the magneto-optic material which is placed in a magnetic field, which is known as the basically Faraday effect. And here the rotation is basically the proportional to the intensity of the component of the magnetic field in the direction of the propagation of light. So when a magnetic field is applied, here a double dispersion effect is generated. Okay, and this basically here the left and right circularly polarized light components must be present and have different refractive indexes. Okay, so when it is induced, so these components will combine to give an elliptical polarization whose major axis is rotated related to the original direction of the polarization, and that's why the angle which is created over here is called the Faraday angle, and it is represented by this theta f. So that can be written by this instruction: theta f equals to kVHL, where theta f is the angle of rotation, which is in radians, h is the magnetic flux density in the direction of the propagation, L is the length of the path where the light and the magnetic field both are interact, and kV, that is the Warded constant of the material. So here the birefringence basically, which is the change of the refracting index, it is related to the angle of rotation by the equation given as this theta f equals to the change of the refractive index or into the pi L by lambda. Okay, and the intensity of variation which is associated with the birefringence, and it is given by this equation: I equals to I0 sin square theta f. Another effect can be seen like void effect. So the magnetic here what happened, the magnetic field which is directed perpendicular to the optical path of the linearly polarized light, which is seen in normally in seen in the gases medium. So this effect is very small in um, paradiamagnetic materials, and the birefringence, which is the change of this refractive index del mu, it is related to the angle of rotation theta v by the equation, this equation. Okay, and same type of effect that can be observed in the liquid, but that effect is called as the cotton molten effect. That is not that will not be discussed over here. Now in reflection mode, the Kerr effect is observed, and it deals with the reflected light from the surface of a magnetized material. And there are three different configurations of light with respect to magnetization in the sample. One is the polar Kerr effect, another is the longitudinal Kerr effect, another is the transverse Kerr effect. And all these diagram has been given over here, you can see it. So in polar Kerr effect, the direction of magnetization is perpendicular to the reflection surface and parallel to the plane of incidence. Okay, but in longitudinal Kerr effect, here the magnetization vector that is parallel to the reflection surface and plane of incidence. Now the incident light that is parallel or perpendicular to the plane of the incidence, this reflected, this polarization of the reflected light, that is elliptical in nature. Okay, and in case of transverse Kerr effect, the magnetization vector, which is the perpendicular to the incident plane and is parallel to the reflecting surface. Okay, so here no change in direction of polarization is observed, but a variation in the intensity or of the intensity of that particular reflected light that can be observed. Now in absorption mode, there are two configurations occur. One is the uh, circular magnetic dichroism or linear magnetic dichroism. So in circular magnetic dichroism, what happened? This is basically the difference in the absorption coefficient for the right and left circularly polarized light, and this difference changes slightly the spectrum of absorption of a sample which is magnetized in the direction of the light propagation. But in case of a linear magnetic dichroism, the magnetic field that is perpendicular to the beam direction. Next, the magneto-optic materials, like a magneto-optic photonic crystal that uh, that comprises the magneto-optic material, such that the optical response of the device that depends on the magnetization of the magneto-optic material. And the magneto-optic effect that can be enhanced by means of the optical resonance. Cadmium manganese telluride or cadmium manganese mercury telluride can be used as a magneto-optic material. Next, the application of this effect, magneto-optic effect. So one is the magneto-optic sensor, another is the optical switches, which is using basically this magneto-optic effect, another is the light modulators and the magneto-optic deflectors. So these are the applications. So in magneto-optic sensor, what happened? These are based on the Faraday effect, obviously, and light passing through the magneto-optic medium that is under the influence of an external parallel magnetic field, which actually splits into uh, two rotating circular wave, partial wave, which have different phase velocities. Now this results in a phase shift of, for the both waves, while their frequency remains the same. So the phase shift of the rotating circular waves that causes the polarization plane to rotate also, and the difference which uh, generated over here for both waves, that forms an elliptically polarized wave when the light exists from the magneto-optic medium. Okay, or in optical switches, using this magneto-optic effect, the analyzer angle, which is beta over here, this one, that is related to the initial polarization that can be made equal to the uh, Faraday rotation, which is equivalent to this theta f L. So that for one magnetization direction, this theta f L, the transmitted light will be extracted from the, and for other direction, the transmitted intensity must be there. Okay. Different light modulators and magneto-optic deflectors can be used. This magneto-optic deflectors means using the this linear magneto optic dichroism or the circular magneto dichroism that can give insight on band structure of the different crystals, and that can be used to design this magneto optic deflectors. Next is the acousto-optic effect. Uh, so basically, it is the interaction between the sound wave and the light waves in an acoustic optic medium, and essentially it is the diffraction of laser by ultrasound. So this is based on the change of the refractive index of an optical medium due to the presence of sound waves in that particular medium, and that's why the sound alters the refractive index of the medium and therefore modifies the effect of the medium on the light. Okay, so sound is a dynamic strain involving molecular vibration that takes the form of waves which travel at a velocity determined by the medium. So when it is passed through the fluid, so compressions and rarefactions are produced, and in those regions where the medium is compressed, the density is higher and the refractive index is larger, and where the medium is rarefied, the density is smaller and the refractive index is also small. Now that is happened in case of fluid, but what happened in a solid? The sound involves a vibration of molecules about their mean position, which alters the polarizability and consequently the refractive index. So that's why the medium becomes a dynamic graded index medium. Okay. So in this context, we need to familiar with the Bragg's diffraction. So a set of parallel reflectors, these are used to separate, these are basically separated by the wavelength of sound, assume this lambda, and that will reflected the light if the angle of the incidence theta occurs, and it satisfies the Bragg's condition for constructive interference, and that can be expressed using this equation sin theta equals to lambda b by 2 lambda. So where the lambda b is a wavelength of incident light, and this lambda which is equivalent to the wavelength of sound. Now, this form of light sound interaction is known as Bragg diffraction or Bragg reflection or scattering also is called. So the device that produces this effect is known as the Bragg reflector or Bragg cell. Here the list of different materials which are used to generate this acousto-optic effect. Silica, few silica are used, lithium niobate is used, arsenic trisulfide is used, tellurium dioxide, telluride glasses, and gallium phosphide can be used. So the selection of this acoustic optomaterial depends upon the specific application. Now, an acousto-optic material suitable for one application that may not applicable for another. As for example, gallium phosphide that is useful to make modulators and deflectors, but not that is not suitable for filter purposes, since it is optically isotropic. That's why. That is the reason. So various acousto-opto effects and their application devices has been enlisted over here. So like different effects like deflection, intensity variation, frequency shift, or filtering, those are used in some application. These are the devices where these are used. So basically this deflection means the angular deviation in the diffracted light beam, and which is obviously the proportional to the acoustic frequency. That is called the deflection, and that is used in acoustic reflectors or routers or switches and optical scanners. Second effect is called the intensity variation. Means the refracted beam intensity, that is the function of the acoustic power, and that application is used in amplitude modulators and different Q switches. Third effect is called the frequency shift effect, that is introduced by the acoustic interaction, okay, using the acoustic frequency, and that is used in fixed or variable frequency shifter. Fourth is the filtering. So here the wavelength selection that can be carried out with large spectral band sources, because only one wavelength will match with the condition. Okay, and that is used, that this condition that is implemented here to design this to make the device called a tunable wavelength filter or different or isolators. Isolators. Now the application of this acoustic optic effect is in acoustic spectrum analyzer, where a sound wave containing spectrum of different frequencies uh, disperses the light in different directions with the intensity of deflected light in a given direction, which is proportional to the sound component at the corresponding frequency. Okay, another application is in case of optical router. So here an acousto-optic cell that can be used as an interconnection optical switch that routes the information carried out by one or more optical beams to another one or more selected directions. So here that cell, which is frequency of the acoustic wave, which is one of the impossible values like f1, f2, f3, like this, and so it deflects an incident optical beam to one of n corresponding directions like theta1, theta2, theta3 in this way. So by applying an acoustic wave of frequency, assume fi, the optical beam is deflected by an angle like theta I and routed to the point in this position. Okay, so that is the application of optical router. So that's all for today. If you have any question, any doubt, you can ask me now.